Welcome back. Let's continue this and let's finish up with asymptotes of a rational function. So, the next thing we need to kind of understand is as the functions get complicated, because 1 over x and 1 over x squared, which is our basic block functions, aren't that complicated. So, we're able to figure out all the nitty gritties that we needed to know to be able to sketch a good function. However, when we have a complicated rational function, looking for the end behaviors becomes a little bit complicated. Trying to figure out what is the horizontal asymptote or thinking about the near behavior around a certain x value, it becomes really, really difficult to figure out. So, what we're going to try and do is kind of break things down so that we can find a way that we'll be able to find the horizontal and vertical asymptotes. However, the concept is still the same. If you think about horizontal asymptote, the idea was we want to approach positive or negative infinity to see what the y value looks like. And then with the vertical asymptotes, we were examining the near behavior around a certain x. So you can think about it as x approaches a minus, or from the left, what does the y value look like? Or as x approaches a from the right, what does the y value look like? So let's dive straight into it and let's see what will happen. Then we can switch back to the notes and kind of make sense to what's going on. Okay, so for example, I have this function here that I want to try and find its horizontal asymptote. F of x is equal to x squared plus 2x all over 3x squared plus 4. So let's apply the concept over here. The rule says that I'm trying to look for, to find the horizontal asymptote, I need to figure out what's going on with positive and negative infinity. What does the y value look like? So I'm going to arbitrarily put in f of positive infinity. So you think about any big number. When you plug this in, we end up getting infinity squared plus 2 infinity all over infinity squared plus 4. Well, it turns out that I'm getting infinity over infinity. I didn't end up getting a number. All I ended up was getting two symbols being divided. So let's go back and analyze what's going on with each of the terms in the numerator and denominator. If you look at the numerator, we have x squared plus 2x. As I'm going to positive infinity, which of these two terms is racing faster? Which is the dominating term in the numerator? Your guess is right. It's x squared. X squared is the dominating term. That is what is making this function what it is. Likewise, when I look at the denominator, what is the dominating term in that denominator? What is driving that denominator? It's the 3x squared that's driving the numerator. So we can ignore the other terms and just focus our attention on just those leading terms. So now I have a function f of x is equal to x squared over what? Over 3x squared. Now, if we clean that up, we end up getting 1/3. So now let's check it out again. F of negative infinity or positive infinity, what is happening? I end up getting 1/3 because there's no x to plug in. So anytime I'm going to positive infinity, it looks like the graph is getting closer to 1/3. How about negative infinity? It looks like it's also getting to what? 1/3. So we can clearly say that as x goes to positive or negative infinity, y is approaching 1/3. All right, let's call this case 1. Now let's look at case 2. I have this function f of x is equal to x squared plus 2x all over 3x cubed plus 4. All right, almost similar. Now, let's do the same analysis. If I plugged in positive infinity or negative infinity, because we can check both ends, we can see that as I do plus or negative infinity, it looks like if I did positive infinity, I'm going to get positive infinity divided by positive infinity. I get positive infinity. If I think about negative infinity, if I plug it in, the numerator still becomes positive, but the denominator becomes negative. So I end up getting positive or negative infinity over what? Over infinity. So again, I'm still getting a symbol divided by symbol. I got to go back and analyze really what's going on in that function. So if you look at that function very carefully, the dominating term is x squared, and the dominating term in the denominator is 3x cubed. So let's pull down, because that's what's driving this rational function here, both in the numerator and denominator. So let's look at it again and analyze it from this perspective. I have 1 over f of x is equal to x squared over 3x cubed. When you clean up that expression, we end up with 1 over 3x. So now let's test it out. If I do plus or minus infinity, as I approach plus or minus infinity, what does this look like? It looks like 1 over 3 to the infinity. That's 1 over a very big number that goes to 0. Likewise, if I tried it with 1 over 3 times negative infinity, I get 1 over a very big number that is also going to what? That's also going to 0. So we have this scenario over here that as x approaches positive or negative infinity, y is approaching 0. Let's look at case 3. So case 3 is this. If I have f of x is equal to x cubed plus 2x all over 3x squared plus 4. Now let's see what happens. If I try plus or minus infinity, let's see what's going on. I'm going to get infinity over infinity if I have positive infinity, if I'm approaching positive infinity. And if I'm approaching negative infinity, I end up getting that. So this is going to both positive or negative infinity. Again, I'm dividing a symbol divided by symbol. Can't divide that. So let's go back and analyze what's going on in the numerator and denominator. So if we look at what's going on in the numerator, the most dominating term is x cubed for the numerator, and the most dominating term is 3x squared. So now let's clean this up a little bit. Let's use just those because that's what's driving that rational expression. 3x squared. That cleans up to be x over what? Over 3. Now let's see what happens. F of x, as I go to plus or minus infinity, it looks like when I'm going to positive infinity, you're getting infinity over what? Over 3. That is still a big number, all right? So that's still going to infinity. And then if you test it with the negative infinity, you're going to negative, so you get plus or minus infinity. So it looks like as I'm going to positive infinity or negative infinity, the function, the y value is approaching what? Positive and negative infinity. So I have this scenario over here. As that goes to positive or negative infinity, y is approaching positive or negative infinity. So we get these 3 cases. Let's see what we got over here. We know from the first case over here that we have a horizontal asymptote at what? Y equal to 1/3. In the second case, we have a horizontal asymptote y equal to 0 is a horizontal asymptote. And then the last one over here, remember that when we say horizontal asymptote, I'm approaching a certain line. In the last case, we are not approaching any line. As x is getting bigger, y is getting bigger. As x is getting negatively large, y is also getting negatively large. So there is no line that the curve, the graph gets closest to as you're looking at the end behavior. So over here we have no horizontal asymptote. All right. Clearly, you can see that it's a lot of work trying to figure out horizontal asymptotes. However, there is an easier way. Let's examine the domains. Let's look at case 1. And let's examine the degree of the polynomials in the numerator and denominator. If I look at the first case, which was x squared plus 2x over 3x squared plus 4, the degree of the numerator is 2. The degree of the denominator is 2. So you can clearly see that when we said y is equal to 1/3, that kind of came from the leading coefficient. Let's use a different marker. It looks like it came from that leading coefficient and that leading coefficient over there. All right. There is a 1 over there. Let's draw the 1 over there so that it makes sense. So it looks like if the degree are equal, we can just pick the coefficient of the leading term. So here y equal to 1/3 is the HA. Now let's look at case 2. In case 2, we had f of x is equal to x squared plus 2x all over 3x squared x cubed plus 4. Now if we do the same thing, the degree of the numerator is 2 and the degree of the denominator was 3. Now this is what happened. When the degree of the numerator is less than the degree of the denominator, then we're gonna say that the horizontal asymptote is always gonna be equal to y equal to 0 because the numerator isn't racing as fast as the denominator. The denominator is always gonna race faster, so it's gonna be a bigger number than the numerator. So 1 divided by a big number is always going to give you 0. So we're going to make this claim that if the numerator's degree is less than the degree of the denominator, then the horizontal asymptote is always going to be equal to 0. So that's case 2. And then the last case is when f of x was x cubed plus 2x all over 3x squared plus 4. The degree of the numerator is 3. The degree of the denominator is 2. You can clearly see that the numerator is always racing faster than the denominator. There is no way that the denominator is always going to be bigger than the numerator. So you get a bigger number divided by a small number, you always end up with a big number. So here we have no HA. So this is a simple way by comparing degrees for the numerator and denominator. On the left side is the hard way, which is you kind of going in depth and kind of figuring out what's going on as you go into positive infinity or negative infinity. So let's refer back to the notes and see what this is saying. So it says that by dividing both numerator and denominators by x to the n, we can show that the horizontal asymptote is always defined by the leading coefficient of p and the leading coefficient of q. So if you look at the scenario over here that they've given, if the degree of the numerator, which is n, is bigger than the degree of the denominator, then r, which is the function, is going to have a horizontal asymptote at y equal to 0 all the time. If the degrees are equal, then that function is going to have a horizontal asymptote at y equal to a of n, the coefficient of the leading term in the numerator, over the leading coefficient of the denominator. And clearly, if the numerator is greater than the denominator, then you have no horizontal asymptote. Okay, so let's look at the examples that they have. So if you look at the example that they have here, they got 3x squared minus 2x minus 1 divided by 3x squared plus 3x minus 2. If you look at the degree of the numerator is equal to the degree of the denominator. So we're going to pick the leading terms, and that becomes what? That becomes the HA. So HA becomes 3 over 2 is equal to y. All right, now they talk about horizontal, vertical asymptote. We'll get to that in a minute. All right. Oh, they actually did that on the other side. So let's look at how we find vertical asymptote. So vertical So to find the vertical asymptote, it looked like we always went to the domain and we analyzed the place of the x values where it was undefined. So we're going to use that and help us to find vertical asymptotes. It seems like it's just like finding the domain. So we're going to do exactly the same thing. We're going to look to find the domain of our rational expressions, and wherever the function is undefined, we have a potential vertical asymptote. All right, so if I had f of x is equal to ax plus b divided by cx plus e, and ax plus f, then we are saying that, well, the domain for this expression here is x belongs to all reals except minus e over c and minus f over what? F over a. So we are saying that these exceptions are potential vertical asymptotes. And I'll explain why I'm using potential. But for now, based on our analysis that we have done in our previous homework, we can claim that our vertical asymptotes are going to be x is equal to negative e over c, or x is equal to what? E f over what? F over a. So in other words, we're looking at the denominator and trying to find where is it equal to 0. And that's how we kind of did domain of rational functions or rational equations. So we're using the same, we're just drawing from our prior knowledge that if you have a rational function, then the vertical asymptotes are going to be the places where the function is undefined. In other words, we're looking at the place where the denominator is equal to 0. All right, so finding vertical asymptote is not that bad. All right, so if you go back to the example over there, they solved for the places where the factor is equal to 0 for the denominator, and they ended up with these two numbers over here, one there and one there. So there are two vertical asymptotes, and then there is one horizontal asymptote. Okay, So we have enough tools now to kind of get into graphing of rational functions. All right, that is it. I hope you're able to make some good notes. See you in class.